Okay, I hope everyone can hear me. Hello, everyone. My name is Giray. This is my name. It's a bit hard to pronounce, but this is Giray. So today I'll talk about some memory security, reliability, and safety problems and some solutions in the recent years and starting from actually early 2010s or even 2000s. So this paper will be mostly about, this talk will be mostly about RowHammer and in general memory reliability. Okay, good. So before we start, I'd like to remind again that we have an upcoming Software Live seminar next Tuesday at 6 p.m. Zurich time. So this talk will be about the bit flips that are observed in some neural networks and their effects and how to get rid of them, what to do about them. So we will be hosting Yanjin Lee, a professor in University of Chicago, and she's quite expert on this topic, and I'm excited to hear what she has to say. So please attend if it fits into your schedule. So today we will talk about reliability, safety, security, and as Professor Mutlu usually does, I also want to start with this bridge picture that looks like a really nice bridge, really stable, and it seems like secure. But then some mistakes in the design or execution or environmental conditions, something happens, and these bridges can collapse, right? So this is a huge problem in terms of reliable security and safety. And we definitely don't want this kind of accidents to happen in our computing systems. So another question is like, how secure are these people, right? So they seem like quite relaxed and they're just like sitting there. There's nothing wrong, but we shouldn't forget that security is about preventing some unforeseen consequences. So we need to be a bit conservative about things. And you can see another picture from Mr. Bean that seems like this car works really well. There are some control surfaces over there, but it doesn't feel very safe and secure. So there can be unforeseen consequences. And today we will focus on a little bit, pretty much on RowHammer. And to like briefly introduce RowHammer, we can say that RowHammer is a phenomenon where one can predictably induce bit flips in commodity DRAM chips. And when you look at the DRAM chips in the market, based on some data in 2014, I believe more than 80% of tested chips are vulnerable to this reliability or read disturbance issue. So this is really the first example of how a simple hardware failure mechanism can be actually exploited, and it can create a widespread system security vulnerability. And then you see some popular science kind of blogs saying that forget about software, now hackers are exploiting physics. So this actually is not really a surprise for the research community. When you look at like earlier papers, this is a paper from 2013, there were already some concerns about what to expect from this aggressive technology of scaling. You keep hearing that we put like more and more transistors into the DRAM chips or like in any chips basically every day, and the technology is scaling down to like a few nanometers, and this comes with some consequences, and this is actually expected way before. So, okay, since we're talking about RowHammer, let's focus on the DRAM background a little bit. So you already heard about DRAM background yesterday, I know, but I'd like to just like quickly recap. So in DRAM, essentially, how you store a bit of data is a voltage value on a capacitor. So this capacitor holds like a high voltage or low voltage, and it means a bit of 0 or 1 to you. And then to access this capacitor, basically you have a bit line, you have some sense amplifier, and you have some transistor here. So this transistor opens the gate, and then you can access the capacitor, the voltage on the capacitor. But the thing is, this capacitor actually is a leaky structure. So it doesn't have very high retention time. And this is an intrinsic limitation of DRAM. And scaling beyond 40, 35 nanometers in 2013 was expected to be challenging. And today we see actually those challenges coming up to surface and creating some problems for us. And this was already another paper in 2015 published in DSM that actually looks at how reliable memory in like some scale-out servers. So this is a piece of data collected from some Facebook servers worldwide. And you can see that as the chip density grows on the x-axis, you keep seeing more failures in servers. And this is because of all this like worsening reliability with technological scaling. And there's another paper here. Oh, this is the same paper actually. Yeah, analysis on modeling of memory errors found in all Facebook servers. This is the takeaway. And yeah, you can access this paper here. I'm not going to cover it in detail. So for the sake of this, what time is it? Sorry. Okay. For the sake of this talk, we need to talk about a bit how to understand the reliability of real DRAM chips, basically. So, so we have a lot of DRAM chips today in the market, and they satisfy some conditions specified by the consortiums, and they seem to work reliably, just like those men sitting on the construction seem to be like really reliable, safe, and secure. But what's going on inside the DRAM chip is still a mystery to some extent. So we need to understand what's really going on and what are the reliability characteristics of these DRAM chips. And we need infrastructure to understand these issues. So there are a lot of infrastructures today available. And there are a lot of works built on using these infrastructures. And this is a good example, Philippine Bits paper from ISCA 2014 that I'll talk about. This is the first paper actually showed that RowHammer is a widespread problem. And this was enabled by this kind of infrastructure, basically. Yeah, this is a picture of a set of FPGA boards that we have, and we have some DRAM chips connected to them. And this is a heat chamber. We control the temperature. We access these DRAM chips in certain access patterns, and we initialize them with certain data patterns. And as a result, we test their reliability, and we understand what are their limitations. Okay, so here you can find more information about this infrastructure. Actually, we have an updated version of that as well called DRAM Bander. I'm going to talk about that as well. So this is a flexible, easy to use infrastructure that you can also use today to, test different things in DRAM chips, push their boundaries. Okay, so this is the full reference. And this is the newer version of DRAM SoftMC called DRAM Bander. So this is actually published just this year, and it's quite up to date. It supports DDR4 and HBM chips now. You can test all those. Just like contact us if you're curious about any particular reliability aspect of DRAM chips. Okay, so yeah, we already ported this DRAM Bander infrastructure to different boards. You can see like different pictures here. It supports DDR3, DDR4, and now HBM as well, even though it's not written here. Okay, so yeah, so we're gonna go back a little bit, a step back, go back to 2013 paper. So I talked about these reliability issues observed in Facebook servers, right? So when the researchers at that time looked at why it was happening, it was relevant to this retention time profile of the real DRAM chips, and also the leakage, read disturbance, data pattern dependency. There are a lot of factors, of course. So at the time when people built these infrastructures, they got curious about about the limitations of DRAM chips again. And the data retention is an intrinsic limitation of DRAM chips, right? So they leak data, and they lose data after some time. So they wanted to understand what are the limitations of this. And this is a paper that actually shows it turned out to be quite useful. Actually, it's still it has still impact on today's cutting edge research. And you can see that like you refresh a DRAM cell every 64 milliseconds based on the specification. But in fact, actually, the vast majority of the DRAM cells can retain data more than 256 milliseconds. So you're actually doing something unnecessarily time consuming and energy consuming. And it's like there's no actually need for doing that, right? So this paper actually brings a lot of performance benefits by relaxing this restriction. And this is only possible by understanding these limitations. Okay. So this is the full paper that talks about that variation in retention time. And I already said that it had like some great impact. You still see today like a lot of papers working on the same topic and building on those findings of that time. So this is another paper, for example, published in ISCA 13, and got an recognition, let's say, in ISCA's 50th year anniversary this year. ISCA is one of the top venues in our field. So it was invited to be presented again in that conference, basically. Yeah, there's another paper here from Sigmatrix 14, DSN 15. There are a lot of works that we will talk in the following lectures. So today we will not talk about data retention time so much, but I'm just showing some papers and leaving the references here so that you can check out these papers if you're curious. So you can see like there's another paper in ISCA 17 that talks about like how to dynamically understand on the runtime, basically how you understand the data retention characteristics of DRAM chips. And in recent years, we see that DRAM manufacturers start implementing some error correction codes inside the DRAM chips, so they're completely obfuscated from the user. And now we have some research in starting from 2019, I guess, but in the upcoming years as well, like in 2021, all about understanding these error correction mechanisms as well and their capabilities. So there's a long lecture already on this YouTube, this video, so you can go check that out. But I believe that next week we will also talk about DRAM refresh and data retention. So let's go back to our topic, RowHammer. So this is a curious phenomenon. So this is how it happens. I'm not sure if you're familiar. How many people are familiar with RowHammer? Okay, 1, 2, 3, 4. Really good. So I'll still cover this. So in modern DRAM chips, your DRAM cells are organized as a two-dimensional array, right? So each rectangle here is a row of cells. So you access a DRAM cell in a DRAM row granularity internally. So to access a DRAM row, basically, you need, to access data in a DRAM cell, you need to activate or open the row that contains the DRAM cell. And then when you're done with that data, you want to access another data in another row, you need to close this. And then if you keep doing this many times, okay, yeah, now you start seeing some bit flips in the physically adjacent rows. And this shouldn't happen. This actually breaks a really fundamental security primitive called memory isolation. So based on this primitive, let's say, or concept, so what essentially you need to guarantee in a computer system is you have like two users, and one user keeps accessing its own data. It shouldn't affect anything about other users' data, right? Otherwise, you compromise some security, you compromise your reliability, you lose a lot of guarantees in your computer system. And this is really a problem. And what we see is that this happens in real DRAM chips today. So we called this middle row hammered row or the aggressor row, and the rows that are affected as victim rows. So this is just the terminology. And when we repeatedly read from the same row, we start seeing bit flips. And today, even we keep testing DRAM chips, and this is really a widespread issue. So this is data collected between 2012 and 2014 from the off-the-shelf DRAM chips of that time. And you see like most of the DRAM chips are affected, actually, more than 80% in DRAM chips from 3 major manufacturers. So these manufacturers cumulatively actually holds more than 97, 98% of the market. So if you go buy a DRAM chip randomly from any store, like go to Galaxus, for example, you will probably end up having a chip from these manufacturers. So something curious again. So this study actually tested DRAM chips manufactured in different years, and if you notice, like up to 2010, actually, these DRAM chips don't show any bit flips. So on the y-axis, you see the number of erroneous cells, right? And starting from 2010, it's the first appearance of this kind of errors, and then it keeps increasing a lot. So the newer chips give you more bit flips. So error correcting capabilities are also in a question now. So why is this happening? This is happening because DRAM cells are too close to each other with technology node scaling, and they're not electrically isolated completely from each other. So when you access one, it actually creates some noise on the electric signal or the charge stored in the other cell, and it exacerbates the leakage, and you end up losing the data. Okay, so it definitely has some higher level implications. So this is a really like phenomenon that happens in the physical level, like in the electrons and devices level, right? But it's actually, so the current research, I will show a lot of examples, shows that it actually affects like the whole computing stack. And now your programs, algorithms don't work reliably, and you can lose some sensitive information. Your computer or mobile phone can get hacked. So this is a simple program. For example, in the user level, you basically keep accessing two pieces of data, and you add an instruction called CLFlush that basically pushes your data from your cache back to the memory. And you end up accessing to the same memory location over and over again. And this simple, like 5-6 lines of code actually is enough to induce these bit flips. Okay, I'm not gonna go through this like really deeply. I guess it's obvious. So you keep accessing X and Y and you see bit flips in between. Okay, so this work that was published in 2014, Flipping Bits, actually showed that on real systems that implement these CPU architectures of that time were already vulnerable, and they observed like thousands of bit errors, and they with these access rates written on the right side. So this Flipping Bits paper was really a big deal. It's still, in my opinion. And it created an immediate impact in the field, and not only the academic research, also in the industrial research. So just like 1 year after this was published, Google Project Zero actually did some experiments themselves, and they showed that you can actually use these bit flips to gain kernel privileges in a system. Basically, it means taking over the system, right? When you have pseudo permission, you can't do anything. Okay, so this is an example of RowHammer security attack. You basically first understand your DRAM chips reliability limitations, basically, and then you test some systems, and you basically aim to induce those bit flips in the page table entries. And in page table entries, there are some bits that identify which user has write permission on those pages, right? Once you flip that bit, Now you have the right permission on that. And now you can isolate your privileges to root privileges. And this is, this is DRAM chip module, and pretty much all the chips are vulnerable here. Okay. So there was a blog post that actually intuitively explains this. It's like breaking into an apartment by repeatedly slamming a neighbor's door until the door that you want to open is opened by itself. So I told that this Philippine Bits paper had a lot of impact. So this is another example. So a lot of researchers in the security community also took it seriously, and they started building system-level attacks. So this paper shows that by just a piece of JavaScript code, you can actually induce RowHammer bit flips. And there's another paper showing that you can do this on Android phones and mobile devices. There's another work that uses GPUs in real systems to accelerate this RowHammer attacks, basically. And another one that doesn't even require you to go and access a machine that you're attacking by yourself. So you basically initiate your attack on another machine, and you send a lot of network packages. And those network packages cause a lot of memory accesses. And by doing that, you can induce RowHammer bit flips. Yeah, this is another example of the same principle, basically. By just like sending network requests, you can take over systems. And this is another more recent example from 2020. So what they do basically in this paper is that they, instead of initiating the attack from the CPU side, they initiate the attack from the FPGA side. And by doing that, they can actually recover private keys twice as fast compared to the CPU-based attacks. So it's not only practical, it's also been optimized to be effective in a very short amount of time. And it's not only used for taking over systems. So this is I really love this example, actually. So this paper says that, actually experimentally shows as well, that these RowHammer bit flips have some data dependency feature. And by leveraging that, you can induce RowHammer bit flips on your own address that is located to a sensitive data that you don't really need to corrupt, actually. Let's say your SSH key is stored in a memory location, right? And you keep accessing that, and you have the data nearby that. So you observe some bit flips in your nearby data. It's basically using your SSH, the SSH key that you're after, like that doesn't belong to you, as a mask on the bit flips you will observe in your own memory address space. So by doing that, you can actually leak information, and this is really like stealth kind of attack, right? So the person under attack doesn't really even notice like there's something going on. There's no failure in the machine or anything, but your information is stolen. There's another one. So we actually keep using these deep neural networks a lot nowadays, right? So these, if you talk about like self-driving cars, for example, or anything basically that uses DNNs, they're already in our lives, and we put a lot of faith on the accuracy of those algorithms or those DNNs resulting in approximately good outputs. And this paper and another paper here, actually, these two are recent papers that show that you can induce bit flips in your DNN's weight. And by doing that, you can reduce the DNN's accuracy from 90% to 10%. So think that, this attack happens on a Tesla car. Now your pedestrian is just like, I don't know, no speed limit, whatever. There's no person over there, just run over, something like that. It's really crazy. Yeah. And it's also used for some other purposes as well. So this is an example that RowHammer is used as a side channel to measure the power consumption in a system or in a DRAM module. So basically, this paper just performs the RowHammer attack. And by observing some characteristics of the RowHammer attack, they can understand if the power load on the DRAM chip is high or low. And this is quite accurate, actually. So it can tell you things like, oh, there's like, the servers are quite busy. So maybe it's a good time to perform your denial of service attack, right? Yeah, things like that. So there are definitely a lot more security implications that are caused by RowHammer. So it's really an important problem. I hope these examples are enough to motivate you. So before going further, I can get some questions if there are any. Or not, I can just go ahead. So all these things are actually summarized in a few retrospective papers written by Professor Mutlu. So you can see the you can access talks and the full papers and the presentation slides here. This is another paper. This is quite recent, actually. Earlier this year, like in January, we did it. So please take a look at these if you're curious. So, okay, let's talk about understanding RowHammer more. So this was the 2014 paper that I kept talking about, right? And it used this kind of infrastructure, tested a lot of DRAM modules from 2008 to 2014, and came up with some characterization results. The first result is that most modules are at risk, more than 80%, right? And you either have RowHammer errors, or you have to stick with the old DRAM chips that work really slowly, and they have like very low capacity. Okay, so this error is somewhat affiliated to charge loss in the DRAM chip, and you need this is a key primitive of RowHammer attacks. You need your victim and aggressor rows to be physically very close to each other. And it also shows a lot of sensitivity studies about the refresh rates, success rates. You can see a lot of details in the paper if you're curious. And it also explores the solution space, how to solve these problems. And I believe I'll talk about them in a little bit. So this is just an example. So on the x-axis, you see the row address relative to the aggressor. So row 0 is your aggressor row. When you keep hammering that, you see that the most of the bit flips are in the immediately adjacent ones. And you can see some other bit flips in some farther rows as well. Yeah, okay. Most aggressors and victims are adjacent, okay. So, yeah, so this is a study that actually looks at like how RowHammer bit flips change or bit error rate changes with the access interval. So how frequently do you need to hammer the aggressor row, right? So you cannot hammer, so this is the interval, so between two activations. It cannot be lower than 55 nanoseconds. This is just like limited by the specifications. But if you increase it, okay, yeah, so it's the other way around, right? So 55 nanoseconds is like the maximum rate you can hammer the rows, and you get the most of the bit flips at that point. And if you make those activations sparse in time, then you get less bit flips. It's actually quite expected. And you don't see any bit flips after like 500 nanoseconds for these chips. But I can tell you that for the most recent chips that we keep testing, this is not really an issue. You can even go for very large intervals, and it's really becoming harder to detect that there's a RowHammer attack going on. It's really a active research area, and if you have like smart ideas, you know, there's a lot of opportunity there. And I think we can help you as well to make those ideas real and have some real impact on the today's and future systems. Okay, so this is about how the bit error rate changes with the refresh interval. So based on the characterization of those chips, if you refresh rows every 64 milliseconds as the specification mandates, you still get bit flips. If you refresh them like sooner than 16 milliseconds, let's say, you don't get bit Phillips for those chips. But today, even if you go like refresh every millisecond, every like tens of microseconds, you can still get bit Phillips, and it's becoming really impractical actually, because you have many rows to refresh as well. Okay. And there's also some data pattern dependency. So if you have some like really nicely aligned homogeneous data pattern on your DRAM chip, which is usually not the case, you get less bit Phillips. If you have some opposite charts stored in like adjacent rows, then there is like more effect over there, and you can get like 10 times the bit Phillips. Okay, so I'll not go through these other observations, but you can check that in the paper. Okay, this is the full paper, and there are some. Sorry, okay, this is another paper. So that paper was in 2014, and it was testing chips up to like 2014. And after 2014, what happened is like for some time, DRAM vendors just claimed that they solved RowHammer. There's no RowHammer issue anymore. Okay, so and then in a few years after that, other researchers started testing DRAM chips. They kept testing DRAM chips actually, and they observed that the things are actually getting worse. So this is an example of that. In 2020, this was also published in ISCA, one of the top venues, showing that basically it's not like it's not solved, and the vulnerability increased a lot over these like 5-6 years. Now you can induce bit Phillips with like 10 times lower hammer counts, for example, even less than that actually. There's another paper here that provides a deeper look into different aspects of RowHammer. So we keep doing research about understanding different aspects of these, and I will talk about that later as well. There's another paper characterizing RowHammer's behaviors under different wordline voltages, because it's all about like hammering the like creating a voltage toggle on the lines that activate the rows, right? When you activate, you put high voltage, you pre-charge or close, you put like low voltage, and that oscillation actually creates a lot of noise. And this is investigating that, like how much of the effect you have when you apply different wordline voltages. And we also have a recent paper from this year talking about RowHammer and HBM2 DRAM chips. So it was not shown before, and people for some reason thought that, oh, our GPU systems are super safe because we use HBM, but it's not the case. In HBM as well, you have RowHammer bit Phillips. So it's really a problem, and we need to talk about solutions as well. Are there questions until this point? There's something on YouTube, I guess. Does memory security apply to the programming language, or is it an architectural issue? So it's really an architectural, it's a device level issue, but it affects the reliability of architecture components, and it has like some outcomes in the user level as well. Oh, Konstantinos already answered. Okay, let's go. Okay, so 2014 paper foreshadows basically two types of RowHammer solutions: the immediate ones and the longer term ones. The immediate ones are to fix the systems that are already affected from this, like already deployed, and you cannot do much about changing the hardware on those systems. So these are like mostly software patches, but they have some limited security guarantees and limited possibilities. So the longer term ones are actually more interesting, because this problem is getting worse, and we need to protect future DRAM chips. So there's a wider range of protection mechanisms here. And our ISCA 14 paper proposed like 7 different solutions people build on top of them. You will see in a little bit. So if we classify RowHammer solution approaches into like some high-level classes, there are like pretty much like 5 of them. So one of the first one is obvious, just like build more robust DRAM chips and or error correcting codes. Okay, it's not really easy though, because technology scaling goes really aggressively. It becomes more vulnerable, and now you try to make chips less vulnerable. It's like it's not really practical. And we don't see that it's happening over the years now. Another one is increasing the refresh rate. Okay, yeah, let's refresh all the rows very frequently. But now you have more rows, and you need to refresh them even more frequently every generation. And you simply don't have enough time with that refresh period to refresh all the rows. Another one is physical isolation. Okay, yeah, let's put aggressor row there. Let's define a quarantine area. Let's put a potential aggressor user to user's data, all of them here. Okay, and let's put some isolation rows in between, and then put our sensitive data far from that. So, okay, it breaks the special relation between them, right? But it doesn't actually work as expected, because I mean, there is no doubt when you put them far apart, you will get rid of the bit flips. But now, with exacerbated vulnerability, you need to put a lot of isolation rows, and it eats up from your DRAM capacity. And the whole point of technology scaling is to put more data into a smaller area. Now you're just like wasting a lot of them, and it's actually working on the other way, right? So it doesn't really some desired solution in that sense. The reactive refresh or the preventive refresh, so-called nowadays, is the most popular one, let's say. So basically what you do is when an aggressor row is rapidly activated or hammered, you go and refresh the rows next to it. So you restore their lost charge again, and they start fresh, and it significantly reduces the probability of observing any bit flips. Another one is proactive throttling. Basically, if you detect a row is being hammered too much, then you throttle the accesses targeting that row, so they will not be hammering too much. But this also comes with a lot of performance overheads. So at the end, when you think about any of these, there is a trade-off space between the cost of the DRAM chip, like cost per bit storage, the power consumption, the system performance, and the complexity you need to implement in your DRAM chips or the processor chips to support all these, basically. Okay, so we keep talking about all these, right? So what did Apple do after 2014 paper? They actually announced that they increased memory refresh rates. Okay, it was a good solution at that time. It's not really a good solution with today's DRAM chips. So we are expecting more sophisticated things, right? Solutions. So this is the first solution that the 2014 paper suggests. It's called para, probabilistic adjacent row activation. The key idea is that you activate a row, and then after some point you close the row, right? Because you need to access another row. Okay, so let's flip a coin, and with some probability, let's go and refresh the victim rows. If you put this probability high, then you go refresh victim rows more aggressively. If you put this probability low, then you do the opposite, right? It's less aggressive. And it turns out that based on the characteristics of the chips around that time, when you apply this kind of probability threshold, you just like go refresh the victim rows once in a while, right? And you significantly reduce the probability of observing a bit flip to this kind of probability. And by changing this threshold, you can play with that reliability guarantee. So basically, para refreshes rows very infrequently, and it is stateless. You don't need to remember any of the access pattern. You don't need to store some complex access pattern data, and you don't need to waste any chip area for that. So it's an effective and low overhead solution to prevent disturbance errors. And if implement, so okay. So basically, I guess in the next slide, actually, I will show that. So Para is quite easy to implement in current systems, and it's actually implemented in many systems. And it can squeeze in all those like necessary victim row refreshes into some idle times in the DRAM chip. And it can be actually done by leveraging some slack time you have in the DRAM specifications as well, or the idle time in between your memory requests. And it can be implemented in the memory controller or DRAM chip. So if you do it in the DRAM chip, you don't know like when the request is going to come, right? But there are a lot of works actually showing that when you do a particular operation in DRAM, let's say you activate a row, you need to wait for some time for that operation to complete. And that actually, the value specified in the documentation is actually much larger than the latency you have in the real DRAM chip. And you have sometimes like in between. So you can leverage that. And if you do that in the memory controller, you can just observe or predict the idle times. You can leverage those. And you can just squeeze in these in a very low performance overhead. And this is what is done in some, I believe, Intel chips. So you can go to BIOS settings and you can change your DRAM refresh settings to, let's say, double the refresh rate, or this is like probabilistic refresh, the hardware RHP. And it actually allows you to set this probability threshold, basically. So it's actually implemented and it had some impact. And I, again, want to encourage you to read this paper. And I can say today that maybe this is not the best solution. Maybe this is the best solution that we have today, but we definitely need like better solutions, because as the chips are getting more vulnerable, it's really hard to keep the performance overhead of this kind of mechanisms low. So a takeaway from this is that main memory needs intelligent controllers so that we can ensure security, safety, reliability, and scaling. Okay, so it's around 2 now. Should we stop a little bit or like go a little bit more? Okay, a few more slides now. So I talk about intelligent controllers here, right? So we already have these intelligent controllers in some other memory technologies. If you look at like NAND flash chips, for example, there's a huge sophisticated controller over there that does a lot of maintenance operations without you even noticing. And it actually makes SSDs quite reliable, while the underlying technology is not that reliable, and you really need some sophisticated error correction capabilities there. And all these are, again, discussed and covered in these retrospective papers. And okay, so based on this, I guess this is the last slide before the break. So going forward, we need to keep pushing in 2 major directions. And this is really important for having some reliable systems. The first one is understanding RowHammer and other variants, basically, of read disturbance error mechanisms and other vulnerability issues. So many effects are actually characterized, tested. We have a good understanding of RowHammer, but we need more. So we still don't know how the agent of DRAM chip affects RowHammer vulnerability, or how does it vary under different environmental conditions, and how does it vary with like, can we find more effective memory access patterns to induce bit flips in an easier way? So this is a really good question, right? This is for like building better attacks and protecting your system against those kind of attacks. And also, solving RowHammer is still challenging. So we need flexible and efficient RowHammer solutions. The key here is to patch these solutions or reconfigure them as needed even after they are deployed in real systems, right? So we need some programmability capability. But when you look at the state-of-the-art solutions, most of them are configured in a way, and you need to basically tape out your chip based on some configuration. And if it turns out that in the lifetime of that processor, let's say, a future DRAM chip becomes like more vulnerable than what it can protect, it becomes really a problem, right? So you need to have that flexibility in some real future RowHammer solutions. And we don't have that. We have that to some extent, but not in some great success. And we also need to start. We actually started. I shouldn't say that, but we should push more on the path to co-architect the system and the memory, because these two things, like when I say system, it's like everything other than memory, right? I mean, you can include that in you can include memory in the system as well, of course. Let's say you have like processor, you have all the other peripherals, you have the whole compute stack, and all of them are tightly coupled with the memory. But with the current communication protocols, your processor is some component on your motherboard, and your memory is something other, and you can even like plug and unplug it, right? And there is a huge isolation in between these two components. And even though they have to work in a tightly coupled way, they actually do not know a lot of things about each other. So this is really a challenging factor in solving RowHammer, and we need to solve it by this co-architecting approach as well. So we will talk about RowHammer in recent years next, but before that, we can take a break, I guess. So until when? 2:10 maybe? Okay. 2:15, okay. Okay, let's get back at 2:15 then. Okay, it is time. Let's get started. Please feel free to interrupt me anytime and ask questions. I would like it more if it's more interactive. We already covered the fundamentals of RowHammer and how it started, how it was exposed to the public, and the immediate impact after that in the first years in like early 2010s and also like late 2010s. Now we will look at the last 3-4 years in a sense. So this is a paper that I mentioned before. It's Revisiting RowHammer. So it's also from our group actually. It was Jeremy's work. The idea of this paper is, so actually maybe I can just go with the slides. So we have many newer chips, and since 2014, we were expecting these DRAM chips to be more vulnerable to RowHammer. So let's see, actually, like let's measure how it turns out. And this is a really good extensive characterization study that tests a lot of chips. You can see the number over there, more than 1,500. And it has a good coverage of the market of that time, basically. And it concludes that newer DRAM chips are much more vulnerable to RowHammer. So you both see more bit flips at a given hammer count, or also you can see bit flips at lower hammer counts as well. So based on the data in 2014, you actually need to hammer a row tens of thousands of times, more than 50,000, 60,000 times to get a bit flip. But now in 2020, we can just hammer like 4,800 times. And this basically gets you a bit flip. To put things into more perspective, I can tell you that in a refresh window, you can perform more than 1.2, 1.3 million activations. And among those, only like 4,800 of them needs to target a particular row, and it gives you a bit flip. So it's really hard to detect among all those activations, right? Okay. So another takeaway is that chips of newer DRAM technology can exhibit more bit flips on more rows and also farther away from the victim row. So the thing that we call blast radius as well, like you hammer a location and then you have a radius of impact on that, right? So it also got wider, and it also studies the existing mitigation mechanisms of that time, and shows that going forward they will be actually not effective. So here's a summary table of the DRAM chips that this paper tests. So it classifies DRAM chips as like old and new based on their manufacturing date and the die revisions. And it looks at DDR3, DDR4, and LPDDR4 chips. And again, from 3 major manufacturers, this is the same set of manufacturers that holds like more than 98% of the market. And different standards, different generations, and yeah, I guess that's pretty much it. And here are some example plots. So there are a lot of analysis in the paper, but I will just highlight a few of them. So here on the x-axis, you see the hammer counts, how many times you hammer a row. And on the y-axis, you see how many bit flips you get. So and the different curves belong to different classes of DRAM chips. So you can see, for example, from blue to yellow, you go from DDR4 old to DDR4 new, right? And if you look at for a particular hammer count, you definitely get more bit flips. And you can also see that, for example, at this location, I hope you can see it. Yeah, at this location so this is the first hammer count that we observe bit flip, right? If we hammer like less than this, we don't observe any bit flip. So this curve actually goes to 0 here. But here, the yellow curve actually observes bit flips here. So a similar trend happens, is there for like all 3 manufacturers. And yeah, you can see that things are getting worse. Yeah. Here is another way, another representation of a similar data. So this time on the x-axis, we have different DRAM types. And on the y-axis, you see the minimum hammer count that is needed to induce the first bit flip in a row. So in short, we call it HC first here. In RowHammer defense mechanisms terminology, we also call it RowHammer threshold. So this is the minimum hammer count you need to achieve to get a bit flip. So this is a box plot, and you can see like there's some variation for all of these chips. It's because like from chip to chip, from row to row within the chip, from bank to bank, you have variations because of a lot of different design choices and manufacturing process imperfections. So not all chips behave the same, right? You wouldn't expect that as engineers anyways. So here we see that variation across different chips basically. And each point within these distributions is showing the minimum hammer count we need. Okay, so what we see here is that if you go from DDR4 old to new, you see that the whole distribution is moved down, right? In LPDDR4, 1x to 1y, so this 1y is like a smaller technology node. It also goes down. If you look at like this one, for example, DDR3, old and new, so you wouldn't observe bit flips, even with like 120K of activations for DDR3 old chips. And it goes drastically down to like 20, 30K. Okay, I clicked by mistake. So it's a drastic reduction, right? You see all these arrows. So it's much more easier today to induce RowHammer bit flips, and it's more practical. And it's good news for attackers, but not for system designers who wants to give some reliable computing system, right? So yeah, so the HC first or RowHammer threshold reduces significantly, and we even see bit flips at only like 4,800 hammers. And I can actually regenerate these results with some other chips as well today. So like this is published in 2020, right? We also test today, for example, chips manufactured in 2022, 2023, and we can easily reproduce this result. And it's like shockingly low, and it's getting lower, and it's like getting more common to see this kind of hammer counts. Please go ahead. 1 second. Could you use the microphone on the table if that's possible? Yeah. You need to press, like hold. So yeah. So basically, we have some control settings. It's not some random measurements on some real system, but it's more like in a controlled environment, we have the temperature stable, and we exactly know like what kind of access pattern we are performing. There's no noise in the access pattern. There's no like, we exactly know like all the timings, all the commands going to the DRAM chip. So we have full control on those, right? But we also test like different, test these chips under like different temperature levels as well. So it's like in hot in like, I don't know, let's say 40, 50 degrees Celsius, 80 degrees Celsius, 85 degrees Celsius, like within these range. Sometimes we go 90, 95 as well, depending on like what we are looking for. So we test in under different temperatures as well. Does that answer? Yeah, so RowHammer is a little bit interesting actually in that sense. So for many error mechanisms, you expect and observe that when you increase the temperature, things get worse. In RowHammer, it's not quite the case. There are a lot of different error mechanisms in the physics level going there that behave differently under different temperatures. And we also have a study actually coming up like dedicated for that purpose. Yeah, I can talk about it a little more when we come to that. It's a fantastic question. So the bit flip direction is, so we observe in both directions, basically. So you can explain this in multiple ways, I guess. So basically, in a DRAM chip, so you have the DRAM capacitor on the bit line, right? So in the closed state, bit line is actually at VDD over 2. So it's like the voltage in between 1 and 0, right? So it can actually leak both ways, right? But there's also this thing called like open bit line architecture for some density optimization, so some specific architecture that's implemented in DRAM chips now. And in that architecture, basically, it doesn't necessarily mean that when you put high voltage into a cell, it means a logic 1, you know? For some cells, it's the opposite. Like when you put high voltage, it means logic 0. When you put low voltage, it means logic 1. So the like bidirectional bit flips can be an artifact of that as well. So it definitely requires like a more rigorous study to definitely answer, you know, there's only like one bit flip direction or something like that. It's clear? Good. Other questions? Okay. So the immediate next thing this paper does is, okay, we saw that things are getting worse. So how does it affect us? So we, from 2014 to 2020, we had like a lot of RowHammer mitigation proposals, and we come up with a set of like state-of-the-art techniques that implement different approaches. You can see the names of those techniques on the top here in the legend, like para. So para is the probabilistic one that I mentioned in the previous hour that we proposed in 2014. So this ProHit and MRLoc are like, again, probabilistic, but they try to improve para a little bit by implementing some counters and having a hybrid approach. And then there is this twice here. It was the state-of-the-art deterministic mechanism at that time. It implements like a bunch of counters, and it tries finding the hot rows all the time by pruning the cold rows, basically, in those counters. So it's a limited set of counters, and they try to detect the RowHammer attack going on. So we evaluated basically these mechanisms here. And what you see in the plot is on the x-axis, you have the HC first, or the RowHammer threshold, in the reverse order, right? So it gets reduced from left to right. So from left to right, we go to future technologies. And on the y-axis, we see the normalized system performance. So if it's like 100%, it means that there's no effect on the system performance. We have the RowHammer mitigation mechanism, it works, and we don't have any performance overhead, right? But as the curve goes low, that means that our system gets slower. And on the y-axis, you see like how much it gets slower. So, and these lines actually mark, okay, these lines mark the minimum RowHammer thresholds that we observe for these these real chips, basically. So we observed up to here, right? So we were still here, and things started getting bad for para, for example. So here you have around like 5-6% performance overhead, I guess. And then we expect it to like get worse as this threshold goes low, because now you need to make things more aggressive. And when you apply the other mechanisms, they also like ProHit and MRLoc are here, but it was not possible to scale that down. Basically, there's a methodology like in those papers. And for twice, it comes out up to like 32K somewhere here. And then after this point, actually, it is not supported by the mechanism. Where is that? I think around like this point. It was not supported by the mechanism, but we just assume that, you know, magically it is supported. Even then, the performance overhead starts getting larger and larger as we go to the right. And this green curve actually marks an ideal refresh-based mechanism. So what that mechanism does is like it exactly knows what's going on in the system. It's a hypothetical mechanism. There's no such mechanism. It exactly knows what's going on in the system, and it performs a preventive refresh operation only when it is needed. And even then, here you see like some performance overhead, right? Some significant performance overhead, almost like 15 to 20%. So this is not really acceptable actually in today's systems, because we keep racing for like 1-2 additional % of speed up. But yeah, this is just like a lot of performance overhead just to make things reliably work, right? It's not really good. And it means that, you know, there's a significant opportunity as well. So things are getting worse. It means that we have a lot of opportunity to develop better mechanisms, come up with better ideas, and solve this problem. And it really brings like good impact. Okay, so on top of revisiting RowHammer, this is the other work that I was talking about actually, that looks at RowHammer sensitivities. So this is published 1 year after revisiting RowHammer basically. And in this work, we look at RowHammer sensitivity to 3 parameters. The first one is temperature. Second one is, you can say like in high level access pattern. What we do here is like when we hammer the aggressor row, we keep the aggressor row open for some time and see the effect of that. And it will be clear in a little while, I think. And also we look at the special variation of RowHammer a little bit and see like if there is any significant difference between which DRAM cell we are attacking. Okay. So we test 272 DRAM chips for this work, and it gives us a lot of takeaways and observations, but we can summarize all of them with this sentence. A RowHammer bit flip is more likely to occur in a bounded range of temperature. I will talk about it in a little bit. If the aggressor row is active for a longer time, not just like hammer it very frequently, also keep it on for some time while doing that. And there is some significant variation basically between different memory locations in terms of RowHammer vulnerability. And we also show in this paper that our observations can directly have impact on crafting more effective attacks and coming up with better defense solutions. So these are the DRAM chips that we test. We again go for like, this time we go for like 4 different DRAM manufacturers. So Micron, Samsung, and SK Hynix are the 3 major that holds like a vast majority of the market. And Nanya is the 4th one. And these chips are coming from like DDR3, DDR4, and different die revisions, different densities. So there's some variation, and they represent the chips in the market pretty much. Okay, the temperature slide is not here, I think. Maybe we'll talk about it next Thursday then. So I promise to explain the temperature effect later on. So I will just give a few examples from this paper. And one of them is the access pattern. So this is known as the worst case access pattern until this paper. So you activate 2 aggressor rows on like both sides of the victim row. So you hammer from both sides, right? So you sandwich the victim row, and you really create a lot of impact over there. And when you do that, when you activate a row, so this is a timeline, and let's say this first black bar is the activation, and the second one is the pre-charge. So you open the row here and close the row here, and you need to wait for some time in between activation, opening and closing to opening. So basically, in this access pattern, you do that as frequently as possible. And if instead of doing that, if you activate row A, wait for some time, like longer than this, and then close, and then activate row B as soon as you can, and then wait for some time, and then close, you can actually reduce the necessary activation count a lot. So what does this mean? So this 36% reduction, let's say you have a RowHammer mitigation mechanism, a completely secure defense, already implemented on your system, and it is configured for some hammer count, let's say 4,800 hammer count. And then you change your access pattern, and now you can induce bit flips at like 2/3 of the activation, that hammer count, right? Around like, I don't know, 3,000 something. And what happens that after all, so your RowHammer defense thinks that everything is going well, so there's no need to do anything, but you end up having bit flips. So it's really dangerous, right? So this is something that was not known until this paper, and it actually started getting a huge impact this year as well. I will talk about it later a little bit as well. So this actually opens up a new dimension in all this like RowHammer field about like solving this RowHammer problem. Okay, so there's another one here that talks about special variation, again from the same paper. So here basically we have on the y-axis the minimum activation count needed to induce a bit flip, and on the x-axis we have DRAM rows sorted from let's say like the least vulnerable row to most vulnerable row. So if you look at this purple curve, for example, this marks the HC first or RowHammer threshold for each row in this DRAM bank, right? And these are just like percentiles from P1 to P99. So you can think of it as some sort of cumulative distribution function. And you see that for this row, for example, we need more than 200,000 hammers to induce a bit flip, which is like quite hard, right? And it's very easy to protect against. But there's also these rows here that actually experience bit flips like less than maybe 50K, 40K, something like that. And you see similar distributions actually in a lot of DRAM chips. So each curve here represents a different DRAM chip. And you see like there's a huge difference in between the maximum and minimum value. And you can see like similar differences for like DRAM chips from different manufacturers actually. So this is something quite important as well and quite useful if you think about it. You don't have to set your RowHammer defense mechanism to be as aggressive for all the rows, right? For some rows, it can be more relaxed. For some rows, it can be more aggressive. So maybe you can reduce your overheads this way. So there are a lot of things you can do by using this. And this is just like a zoomed in version of this. We are just like looking at the last 10 percentile of this distribution, basically the tail of this distribution. So the worst case, for example, hammer count here is 43K, right? For this chip. And then when you look at like, when you get the 10% most vulnerable rows in this distribution, you see RowHammer thresholds between like 43 and 86K, or maybe we can look at it here, between 25K and 50K, for example, right? And for the rest of the rows, the 90% of the rows, all of them have hammer counts larger than 50K. So maybe it makes sense to just like focus on this region, right? Maybe you don't have to worry about the other rows. So it's really important to know about these things so that we can come up with smarter solutions. Please go ahead. So far, it seems mostly just manufacturing process variation. So when you tape out your chips and manufacture them in your silicon, basically, not every part is like identical after production, right? So there are a lot of variation going on there. And I just like the dominating factor is that, because yeah, actually recently I looked at this variation quite a bit and tried to find like some sensible patterns, correlations. Yeah, unfortunately, it doesn't seem like there is a very strong correlation, or at least I couldn't find. And as far as I know, like in the literature as well, it's not found. So if you can find something, for example, it would be something new and really impactful, because in that case, if we know like, oh, there's this design decision that causes like some rows to be extremely vulnerable than others. So there are like things you can do, right? You can just like, you can inform your RowHammer defense mechanism, for example, with that design decisions. And then it will just adjust its aggressiveness based on that. Or even better, you can go revisit those design decisions. You can solve it. You can make them in a way that, you know, your DRAM chip will be less vulnerable to RowHammer. So it's really important. Yeah, thanks for the question. And it's an ongoing research problem, actually. So we definitely need like more people working on this, and yeah, there is really a lot more work to do, really rigorously. Yeah, go ahead.
So you talked about I guess they.
Yeah. Yeah, now you need to store it, you need to maintain that data, you need to make sure that your understanding of the bank is correct, and it will be correct for different conditions as well. There are a lot of challenges there. I guess that's the most straightforward way to, you know, get that mapping somehow and then store it somewhere, keep sending some queries. I guess a better way would be like find some correlations and just like affiliate this characterization, this variation in this characterization with some other feature of the row. And then maybe you will get something much more efficient, like some tinier structure. I don't know. There are a lot of things to do over there. Yeah. Do you have ideas? Okay. So yeah, I'd like to encourage everyone to, you know, keep thinking about this. Sometimes these ideas are like, you see the paper, you think that the idea is like quite obvious. Yeah, of course, this was the idea, and this was the obvious thing to do at that time. But sometimes it's really hard to think about those, you know. Everybody's mind works differently. So yeah. If you have some ideas, I guess don't hesitate to, you know, bring them up and we can discuss, and we can also help you make them realize again, you know, there's a lot of things you can do here. Okay, so in this plot, we are looking at the variation across like columns and chips, basically. So this is one indicator of like, there can be some design decisions playing a role here. Because we see that in rows, like, so this is like each vertical bar here is an aggregated value of, this is based on bit error rates, basically. And this is aggregated across all rows in a chip. And you can clearly see that some columns are actually much more vulnerable than others. So if the color goes like brighter, it means like more bit flips. So on some columns across all rows, you observe more bit flips. So this kind of systematic variation can mean something, right? So we didn't discover it yet. It's another thing that we need to discover. If we can understand this more, we can make use of it. Okay, so here is another slide about the how can we make use of our observations for improving our defense mechanisms. So I already talked about this actually. We know that like 90% of the rows have more than like twice the worst case RowHammer threshold compared to the most vulnerable 10%. And yeah, at that time we did some like back of the envelope calculations showing that we can reduce the area overhead of some state-of-the-art RowHammer mitigation mechanisms of that time by using this variation. Another example is about the temperature. So there was no characterization results over there to save time, but I can summarize it. So basically what we observe with the temperature is that when you look at a particular DRAM cell and it's vulnerable to RowHammer at some particular RowHammer hammer count, and you sweep temperature from very cold temperature to very hot temperature, right? So at cold temperatures, first, you don't observe any bit flips up to some level. And then you start observing some bit flips. And you keep heating up the chip. Now, after some time, you stop actually observing bit flips. So it tells us that DRAM cells are vulnerable to RowHammer at a bounded range of temperature that we call the vulnerable temperature range. And outside of this temperature range, it's like less vulnerable. So don't ask why, because it will take a lot of time to explain at this moment. But I can refer you to some other circuit level papers that explain this in a great detail. It's basically related to some tunneling effect that they hypothesize that, you know, it's playing a role in RowHammer. Okay, so what can be the improvements on defenses? So you can disable or retire some rows in some temperature levels, for example. Let's say if you know that this row is vulnerable between 30 and 40 degrees, and another row is like 50 to 60 degrees. At 30, 40 degrees, you can use the less vulnerable row at that temperature range and vice versa, right? So there are things that can be done. And this is a full talk about this paper. We have a bunch of these actually. You can take a look at them and we can discuss more. Okay, so on top of these, we also looked at how RowHammer varies with the word line voltage. And yeah, this is the infrastructure that we used for this work. And we observed that if you operate your DRAM chip in a way that your supply voltage will be the same, but maybe I can show, no, okay. So basically, if you remember, like there was a transistor in the DRAM cell, right? So you drive the gate of that transistor with the word line. And you provide a separate voltage to that word line, which is usually higher than the rest of the supply voltage of the circuit. And when you open, close, let's say it's around like 2.5 volts in DDR4. You go from 0 to 2.5, back to 0, back to 2.5. So there's a huge oscillation over there, right? And the rest of the circuit is supplied with like 1.2, 1.25 volt. And basically this magnitude of this voltage swing is playing some role basically on the effect of RowHammer. And we show that if you reduce this magnitude, if you drive these lines with like lower voltage, then you can actually reduce RowHammer vulnerability. You observe bit flips at like higher hammer counts now, and when you observe bit flips, you observe like less bit flips. So things can get better if you reduce the voltage. And it comes with some costs, of course. When you reduce the voltage, now your circuit works a little bit slower, and it increases the latency of accessing a DRAM row. And it can reduce the data retention time of that row, so you need to refresh it a bit more frequently. So these things sound like not good, but at the same time, we observe that this increase in the access latency and the increase that we need in the refresh rate are already in the guard bands of the current values actually. So for most of the chips, you can just reduce the word line voltage. And effectively, the chips just works because even though the access latency internally increases, you already like the specification dictates you to wait for a larger latency than that anyway. So it's basically leveraging those guard bands to reduce voltage and improve RowHammer reliability. So it's a quite nice paper. I suggest that because it's my paper. And yeah, you can see a lot of references here. There is a 24-minute talk as well. So you can feel free to take a look at that. Wait, okay, this is another paper. I just skipped this, sorry. So this is another paper that we published in this year in June in DSN conference. It's a short paper. It's easier to read. It doesn't take too much time. And because it was in the disrupt track, which is for like some disruptive immediate ideas. So over there, we basically characterize RowHammer in HBM2 DRAM chips. And we find out that so in HBM, how many people are familiar with HBM, high bandwidth memory? You, okay. Okay, so HBM is it's a 3D stacked memory, and it is more commonly used actually today with FPGAs and GPUs. It gives you a lot of banks, a lot of channels, so it has internally a lot of parallelism, and it gives you a huge bandwidth. So you can so if you need to access a lot of data in a very short amount of time, it's really good. And even with some CPUs, actually, they implement with HBM stack now. And the special thing about this HBM compared to DDR3, DDR4 is that this like 3D structure, and you have like different channels in different dies that are sitting on top of each other. And here, this work is also interesting because of like characterizing RowHammer in that kind of like 3D environment, right? And we show that like there is a huge variation across these channels that are placed in like different dies, and there are also like a lot of variation, which is more systematic in a way in HBM DRAM rows within a DRAM bank. And there's an interesting observation here that we didn't observe in DDR4 chips. Towards the end of a DRAM bank, actually, the last 800 rows in a DRAM bank are actually more RowHammer resilient. You observe like much less bit flips over there. So here you go, there's a bit more systematic variation over here. We still don't know why. We hypothesize that it's because, you know, the placement of those rows and their proximity to the I/O circuitry and things like that. But it definitely requires like more rigorous and in-depth investigation. We also look at if these HBM chips, relatively new, right, compared to DDR3, DDR4, if they implement any RowHammer mitigations inside, and we observe that they actually implement something that we couldn't discover completely yet, that actually uses every 17th periodic refresh to internally refresh the rows that you keep hammering. So it's another interesting finding. And based on these, we will have new RowHammer solutions. Okay, I need to speed up a little bit, I guess. Okay, so this, okay. So I will talk a little bit more about like what is done in terms of solving RowHammer instead of understanding RowHammer. As I said earlier, after 2014, the first public announcement of like how bad and widespread this problem is, people start asking this question to DRAM vendors, like, what are you doing? Like, are you gonna solve this problem? And around, I guess, 15, 16, they start marketing some chips saying that, oh, these chips are RowHammer free and we already solved the issues, so you will not see this RowHammer issue anymore. Just like believe us and buy these chips and you're all right. And of course, some researchers bought these chips and started testing them because we don't believe what they say. So it appeared in 2020, actually, this trespass paper. It's a paper, it's actually a quite good collaboration between Virgin University, Amsterdam, ETH Zurich, and Qualcomm. In this work, like long story short, actually, it basically experimental demonstrates that those DRAM manufacturers were lying, saying that RowHammer was a solved problem. And they show that it's not even like not solved, it's again worse. So there's that as well. So this is the first work to show that TRR protected DRAM chips. TRR stands for target row refresh. This is the terminology that is used in the DRAM industry. These chips are vulnerable to RowHammer in the field, and mitigations advertised as secure are not secure at all. And so this work basically introduces a new access pattern. Instead of you have a victim row and you're hammering both adjacent of this victim row, now you hammer like multiple rows. This is called many-sided attack, and there is a drawing of that actually in the next slide, so I'm not gonna talk about it. So you basically, the key idea is you hammer many rows and you confuse whatever defense mechanism they implement over there. And the mechanism cannot follow you anymore. After some point, it breaks. And by leveraging that, you can actually induce bit flips quite systematically, reliably, and your attack works really well. So it partially reverse engineers the existing TRR mechanisms and exploits that. And it provides an automatic tool that can effectively create many-sided RowHammer attacks actually on DDR4 and LPDDR4 chips. So this is the drawing of this attack. So in the double-sided attack, so let's say your red is aggressor row and blue is your victim row. If you take a look at like x-3, x-2, x-1. So this was your classic double-sided attack, right? So they first try assisted double-sided. So they also hammer some other irrelevant rows in other locations. And they observe that, okay, yeah, so hammering those rows actually helps confusing the implemented mechanism. And then they also even do a better thing. So they interleave across rows. So they keep hammering these 4 rows. So this allows you to confuse the mechanism and also to disturb these rows more because these aggressors are quite close to each other as well. And it turns out that you can have a lot of bit flips, and it varies on how many aggressor rows you use, and it varies from manufacturer to manufacturer, chip to chip, basically. And they tested a lot of DRAM chips again, and they also tested a lot of real systems, including some phones from Google Pixel, Huawei, Sony, HTC, right? Samsung, Xiaomi, Note 8. And on some of them, they found some reliable access patterns, these green ticks basically, that gives you RowHammer bit flips. And these are not quite old, right? Like manufactured in 2016 to 19. So they already know about RowHammer in 14, right? And this is more real system attacks. So this is like how much time it gets to induce bit flips in a page table, how much time it gets to steal your RSA key, how much time it takes to get pseudo permission. And you can see like, okay, in a few seconds, you can do some stuff. In an hour or in like a few hours in different modules, different systems, you can pretty much like do a lot of things, right? You can take over the system, you can steal data. It's quite impressive. And they tested like 42 DRAM modules in this work, and 13 of them turn out to be vulnerable. And 13 mobile phones, five of them turn out to be vulnerable. And this is just like scratching the surface. This is not really a super rigorous characterization study that revealed all the details about these implemented mechanisms. If you figure out more, you can perform better attacks. Yeah, so to my knowledge, I don't know if like, yeah, I didn't see any reports of, oh, this thing happened and this attack has been used in that. Yeah, to my knowledge, I don't have any reference for that. Well, basically, yeah, in a lot of papers though, you can see that it can be reliably done, even with JavaScript code. So RowHammer is still an open problem, and DRAM manufacturers tried security by obscurity. They just said that it's done. They just obscured the problem, and it was not a good solution. It will not be a good solution in the future as well. So we need to understand more. We need to solve better. This is another paper that uncovers these on-die TRR mechanisms. What it does is basically it profiles DRAM chips as data retention characteristics, and based on these characteristics, it attempts to understand. It actually uncovers within a given refresh command if the given row is refreshed or not. And based on this information, it can actually uncover all the mechanisms and algorithms that are implemented inside the DRAM chip. Even though these things are like completely undocumented, right? This is completely obscured. So this is a pure reverse engineering study. And it shows that it tests 45 modules and from 3 manufacturers, like 15 from each manufacturer. And it shows that all of them are vulnerable. And 99.9% of the rows in a DRAM bank experience at least one RowHammer bit flip. And when you observe bit flip, you can observe up to 7 RowHammer bit flips in an 8-byte data word. What does this mean? You have like 64 bits, and you can have like 7 bit flips in that. So usually your ECC implemented inside DRAM is capable of correcting like 1 bit flip and detecting 2 bit flips in the 64 bits. But you have 7 of them. So it's really hard to detect and correct, right? So it concludes that the on-die TRR mechanisms implemented by the manufacturers do not provide security, and they can facilitate the development of new RowHammer attacks and more secure RowHammer protection mechanisms if you understand them. Okay, so I'm not going to go through all these. I already talked about these, and yeah, this is just the distribution of the bit flips across different data byte chunks. Basically, the takeaway is that we can have like many bit flips in a given data word by using this attack. There was another attack from Google. It is published in a blog post in May 2021. And then later on, it became a top paper in a security conference, a top venue. It's called Half Double. Basically, this is completely from industry, right? It's not just academia. Industry people are also working on this. So what Google did was, okay, in the classic RowHammer, we have one aggressor and we have victims nearby it. Okay, let's change this access pattern a little bit. Let's define our rows in a little bit different way. So let's say this will be my aggressor. I will call it far aggressor because this is my real victim. And then this is my another aggressor, that is near aggressor. So you hammer this middle row a lot and this other row a little bit. So what RowHammer defense mechanism thinks is that you hammer this, so it thinks that it needs to refresh this B. So the more it refreshes B, refreshing means like you activate the row, wait a little bit, and close the row. So these refreshes to B are actually counting for the hammer count that you expose to C here. So activating this aggressor A many times because of like some close proximity, it already has some impact on C. It's not enough by itself to induce any bit flip. And you also activate this B a little bit. It's also not enough by itself to induce any bit flip on C. But when you just like have these two effects cumulative, and also on top of this, your RowHammer defense mechanism thinks that it's doing a great job refreshing B, you end up having bit flips at C. So this is a beautiful way of just like bypassing all these mechanisms, right? If they are not designed in a smart way. So usually what you need to do, if your defense mechanism is refreshing B, then you need to count for that as an activation, right? But they didn't do that. And as a result, you have this. And also as a result of this, like this thing called blast radius, activating aggressor A also has an effect on C, but the RowHammer defense mechanism was not accounted for that. So it's really an example of like bad RowHammer defense mechanism being exploited in a very smart way. And later on, it was published in Using Security, one of the top security venues in 2022. These things actually started like attracting a lot of attention, both in the research and industry community, academic and industry communities. And they're emphasizing that RowHammer is really getting more and more important. So we have another paper here, BlockHammer. So this is another solution that we proposed in 2021. I will quickly go over it. I don't want to spend too much time because we are short in time actually. So this paper addresses two key challenges. So one of them is the scalability that we keep talking about. Chips are getting more and more vulnerable, and we need to account for that, right? And the second thing is the compatibility issue. So I can talk a little bit about that. So the compatibility comes in play in this isolation between the DRAM chip and the rest of the system. So when you have a DRAM address, DRAM row address, let's say it goes like 0, 1, 2, 3, right? It goes sequential, but it doesn't have to go sequential in the physical layout in the DRAM chip. And from the rest of the system, you don't see this information actually. So let's say you detected that row n is being hammered a lot, and you want to refresh row n minus 1 and n plus 1, and your defense mechanism is located in your processor. You can send refreshes to n minus 1 and n plus 1. Actually, why am I talking about this? I can just show it here. Oh, it's not visible here, sorry. You can try sending refreshes there, but it's not guaranteed that those n minus 1 and n plus 1 are like physically adjacent to each other. So you can end up refreshing some irrelevant location. And maybe you can even see bit flips afterwards. So it's really a weakness of all these like refresh-based mechanisms. So BlockHammer is trying to come up with an alternative method that doesn't have this problem. So what it does is basically, so your RowHammer attack hammers row A here, and then it detects that row A is being hammered a lot, and then it selectively throttles the accesses that are targeted to row A. So it just like slows down the accesses to row A, but not to other rows. And if you can slow it down enough, now you can guarantee that no bit flips will occur because the total hammer count will not exceed some value. And you can also inform the system software saying that there is this thread, hardware thread, that sends a lot of memory requests to this particular row. It sounds malicious, so take some preventive action. You know, you can just give this feedback to the system software, and then you can trigger some malware detection mechanisms or things like that. And the beautiful thing about BlockHammer is that it's compatible with commodity DRAM chips, because even though we don't have this adjacency information, we actually don't need it here because we don't care about which rows these green ones are. We just like detect that row A is being hammered and we just slow down those hammers. So it has two main components basically. One of them tracks row activation rates, blacklists the row, And then throttles activation is targeting a blacklisted row. And by doing that, it guarantees there's no bit flips. And the other component called attack throttler identifies the threads that perform these attacks and reduces their memory bandwidth usage, even though they are not targeting that particular row. And by doing that, it actually opens up some memory bandwidth for the concurrently running other applications, and it can increase the performance even more. So these are some performance results. So on the x-axis, we have the RowHammer threshold going from high to low again. So to the right, we are going to the newer technologies. And we are looking at like two cases. The first one has no RowHammer attack. The second one has RowHammer attack. So when there's no RowHammer attack, you can see that para is getting worse actually as the RowHammer threshold reduces. But BlockHammer is not affected because it actually detects the attack. And if there's no attack, it doesn't take actions. And its performance overhead is negligible, less than 0.6%. And when there's an attack, all those refresh-based mechanisms are actually exacerbating the situation because there's an attack, your memory is already under high pressure, there's a lot of bandwidth usage, and you're injecting more refresh requests to avoid bit flips, and it's even like overwhelming the memory bandwidth more. And instead, what BlockHammer does is like just like removing some, not removing, but like slowing down some accesses, right? So it opens more memory bandwidth. And as a result, you actually get speed up when there's a RowHammer attack compared to the other refresh-based mechanisms. Okay, that was BlockHammer. And there is another one, yet another one mechanism that, again, this is from our group. It's accepted to the user security of 2024, so it will appear next summer in the conference. But soon, I think you will see this paper on archive, and I think Ataberk will come here and give a lecture about that as well. So here, what we look at is, so the problem is the same, right? RowHammer vulnerability worsens as DRAM becomes denser, and existing defenses become costly. And our goal is to prevent this bit flips with low performance overhead. Okay, so there is a beautiful key observation in this paper. So in DRAM chips, you have many banks, and it gives you parallelism. And you want to use this parallelism in like benign case, right? You want to use this parallelism, so you split your data across these banks so that you can access them in parallel. So this results in a particular access pattern to be repeated across different DRAM banks, actually. So basically, if a row is being activated n times in one bank, its activation count in another bank will be something similar to n, like minus plus delta. And until Abacus, all the RowHammer defense mechanisms were actually implementing a lot of counters per DRAM bank. And the beautiful thing about this idea is that, okay, the banks are behaving similar, so why don't we make the rows across different banks to share the same counters? And when we do that, it actually allows us to achieve high performance, and that the area-hungry counter-based mechanisms already have. I mean, some similar performance at a very low area overhead. So the hardware complexity reduces. Okay, the key result is that when we try this on like many different multi-program workloads for different RowHammer thresholds, we show that it's faster than the lowest area cost counter-based defense mechanism, and it's smaller than the lowest performance overhead counter-based mechanism. So it induces very little performance overhead, and it's really tiny when you compare to other mechanisms. I don't need to get into these details, I guess, for these numbers. Okay, so this is pretty much the state of the art in the RowHammer solution side, but we definitely need better solutions. And I'd like to quickly talk about some more infrastructure. So I already talked about understanding RowHammer and the importance of the infrastructure for that, right? So without those FPGA-based infrastructures, we wouldn't understand that. And for building softwares, sorry, not software, building solutions, we also need a good infrastructure for simulation setup so that we can understand all the trade-offs going on in the memory subsystem. So this is just a quick announcement of Remulator's a new version. This is the simulator that we keep using since very old times. But now there's a newer version that is published recently. So it will appear in contract teacher letters in 2023. And the preprint is already available in archive since August. And it's open source on GitHub. You can access that. And the beautiful thing about it is that it implements everything in an extremely modular way. And when you want to, let's say you want to develop a new RowHammer mitigation mechanism, you can just like add a plugin to the simulator, and it will just like work seamlessly. So this is important because, again, the same takeaway, main memory needs intelligent controllers for security, safety, reliability, and scaling. And we can only do that by like understanding the real chips, understanding the trade-offs in the memory subsystem, understanding all these like effect of these timing parameters and things like that. I think this has been a little bit tiring and we can take a break at this point. But let's keep it short because I need to cover a bunch of other slides. So can we make it like 5 minutes? Let's say now it's 17. Let's come back at 25, 3:25. Is that good? Okay, thanks. Meanwhile, are there any questions? I didn't ask about that. Okay.
Is it possible?
There are proposals, software level proposals. So the common problem with those is that it's really hard to accurately detect that there's something going on. And a smart attacker is usually finding a way to, bypass those mechanisms because you're obfuscated from a lot of things if you're in that level of the system, right? There's a really good paper actually from Daniel Gross. It's called Another Flip in the Wall of RowHammer Defenses. So it's in that paper, they take like all of these kind of defenses of that time and they just like build attacks one by one to bypass all of them. So you see like it shouldn't be really done in that level after reading that paper. I really suggest that it's a good read. Other questions? Okay, yeah, let's take the break then. Thanks. Okay, it's already 25. Sorry if it's becoming too tiring. Last 35 minutes. So I'll cover the rest. I'll try to cover the rest a bit more quick. So let's start with this takeaway again. Main memory needs intelligent controllers for security, safety, reliability, and scaling. And if you remember, like these were the known RowHammer solution approaches until now, basically. And they all have trade-offs in terms of cost, power, performance, complexity. So now I'll talk a little bit more about the advancements in the RowHammer defenses in the recent years. So maybe you don't see raw migration-based RowHammer defenses in this list, but I can actually classify it in the physical isolation part here. So their idea is basically, okay, so we detect that there is a row that's been attacked, and we can go refresh the victim rows, but maybe we don't know which victim rows we need to refresh, or maybe this will be too costly. So what should we do? The idea is to move the aggressor row to another physical row and remap it so that the further accesses to that physical row will be going to the other physical row. So you split the number of activations across different physical rows, even though they are trying to access to the same logical row address. This is published in like ISCA 2019 in Crow, and also in ASPLOS 22 in randomized row swap paper. Yeah, you can see the papers here. So there are some other follow-ups as well based on row migration-based RowHammer defenses. This Aqua was published last year in Micro, and there's also 2 papers appeared in HPCA 2023. So these are quite recent, and all of them are like top venues in architecture community. And finally, we see some publicly available documents, papers, white papers, talking about how to protect or, talking about the RowHammer defense mechanisms from the industry. So SK Hynix has been quite productive about this. So they published this paper, and there is a fairly good explanation of how it is done, and they also show that how it is implemented in the tape-out picture as well. So I guess you can take a look at those. There's another paper that appeared last year, earlier this year, from Samsung. It's also talking about on-die, I guess it was on-die, right? RowHammer defense mechanism. I'm not sure. Okay. So if you look at the papers, so that appeared on like targeting to solve RowHammer in the recent years since 2020, you see like 2 papers in Micro 2020, some other papers in IEEE Security and Privacy Conference, Using Security Symposium, Hot OS. Another Using Security from 2021. The Smash is actually quite interesting. It gets real DDR4 DRAM chips from modern, basically, generations that are supposed to be RowHammer free and induces RowHammer bit flips just by JavaScript. Okay, so there were 2 other papers in Micro 2021. Another set of papers in IEEE Security and Privacy 2022, ASPLOS 2022, HPC 2022, IRPS, User Security, CCS, a lot of venues, right? I'll just like click and move on. I guess, this is the last year's Micro. It was quite interesting, actually. So I'd like to just highlight one paper because it's my paper published in last year Micro, and I will talk about it a little bit actually. It's basically targeting to reduce refresh latency in off-the-shelf DRAM chips so that we can perform RowHammer mitigation in a lower performance overhead. And people are also working on fixing this transparency issue between the DRAM chip, or the isolation issue, let's say, between the DRAM chip and the rest of the system. So there's a nice paper, nice read on archive. I guess it will appear sometime soon as well, but you can go ahead and read it. It's a quite good discussion and positioning about these issues. And here there's another archive paper that tries to fix this isolation issue by proposing some like very minor tweaks in the existing interface. And with these tweaks, we basically enable the DRAM chips to perform all sorts of maintenance operations by themselves without needing to, processors to implement something. Yeah, there are more works in 2023. So here's a snapshot from IEEE Security and Privacy, high performance computing architecture, again from SK Hynix, the same slides. And I guess this is the most recent DSN 2023. We have quite a bunch of papers focused on RowHammer over there. And yeah, there's also symposium on operating systems and principles, and some upcoming computer architecture letters papers and embedded system letters papers also focusing on RowHammer. So you can see that it's like quite up to date and quite important. And I'd like to remind you about Remulator 2.0. You can just download today and start playing with that and develop your own RowHammer mitigations. And if you need help, we are here to help, definitely. Yeah, there are more papers in MEMSIS and Micro 2023. So Micro 2023 didn't happen yet. So we don't have the paper actually yet. It will happen at the end of this month. And I guess, yeah, I want to encourage you to, just follow and read this paper as well. It seems interesting to use like ECC or redesign ECC in a way that it can actually reduce RowHammer bit flips. Okay, so I show you a lot of RowHammer defenses, a lot of works, a lot of different approaches. So the question is, are we now RowHammer free in 2023 and beyond? What do you think? Yes, no? Don't know? Don't care? Yeah, it's hard to say, right? So it's actually not that hard to say. So maybe you can argue that we are RowHammer free. There are a lot of solutions. At some point, DRAM manufacturers will implement these and the things will be solved. But it doesn't stop there. So this is a paper that was published in last June in ISCA. This is also from our group. Hasan published this, and he will talk about it later. This is called RowPress. Do you remember in the deeper look paper, I talked a little bit about the access patterns where you keep the aggressor row on a little bit longer. It makes a difference. So this paper actually makes a great use of it, characterizes it really rigorously, and then discovers a new actually error mechanism or a new read disturbance phenomenon that is different than RowHammer. It works similar to RowHammer, but it is different. It was not known before, and it's now putting a lot of new constraints on designing new defense mechanisms. So this is the full paper with all these resources like slides, talks, and stuff. And I think it's also important to say that this won the Best Artifact Award because like we open source all the characterization data, everything is online, you can go check, and you can see like how bad things are getting actually. So maybe we can become RowHammer free at some point, but it doesn't seem like we will be free from read disturbance and the scaling problems. So this paper demonstrates the RowPress, a new read disturbance phenomenon, and it's different from RowHammer vulnerability, and it can be actually exploited in a user level program. We showcase that, we demonstrate it, and we induce bit flips in real DRAM chips on real systems that are protected by on-die target refresh mechanisms. And we also provide some effective solutions to row press. So basically, the key idea is to keep a row open for a longer time. It's very simple. And these bit flips do not require many row activations. So it's really hard for the RowHammer defense to detect it, actually. And in some extreme cases, only one row activation can be enough to induce bit flips. And yeah, so I will not go into the background. So you remember this animation? We open close, right, in RowHammer. We don't do that here. We basically open, wait, and the bit flips occur. And we close. Yeah. So so mitigations so far are based on like high row activation count. That's how we detect RowHammer attacks. But it doesn't work for this. So what if there's another way? So this is a bypass, basically. And this is your traditional RowHammer aggressor rows access pattern. You open, close, open, close. In row press, you open, wait, 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 close, open, wait, wait, and it induces bit flips. And if you wait like 7.8 microseconds, only 5 key activations are enough to induce bit flips. And this number is for a chip that requires like 47K of activations if you do this like every 36 nanoseconds. So this is the infrastructure that we used, and these are the chips that we test. All these information are available online. And row press significantly amplifies the DRAM vulnerability to read disturbance, and it has a different underlying error mechanism. And I'll talk about how we know about this as well. So, but first I will show how it amplifies the read disturbance mechanism. So basically, in this plot, on the x-axis, you see that how much time we keep the aggressor row open when it's opened. So if we keep closing it after 36 nanoseconds, on the y-axis, this is the minimum activation count. So how many times you need to activate the aggressor row, right? You need to activate the aggressor rows around this time, this many times, if you only kept them open for 36 nanoseconds. If you keep them open 7.8 microseconds, which is the refresh interval, so you can easily reach to this number actually with today's specifications. And it already reduces the activation count a lot, right? And there is actually a relaxed version of the specifications today that is implemented in most systems actually. You can postpone the refresh requests. And this is important because when you send the refresh request, it dictates the closing of the active row, right? So when you send the refresh, you need to close the active row. And you send the refresh every 7.8 microseconds based on the specification. But specification allows you to not to send any refresh for 7.2 microseconds and then send like 8, 9 different refresh commands back to back. So the specification allows that. So you can keep your row open for 70 microseconds and your activation count reduces to this. So we didn't want to stop there and we wanted to see the extreme case. If we keep row open for 30 milliseconds, this is 10 to the 0, right? Just one row activation. You activate, you wait for 30 milliseconds, boom. In the nearby rows, you have bit flips. It's quite interesting. And this was not known like last year, this time, right? So there are many things to discover. So this thing gets worse as temperature increases. This is a different behavior compared to RowHammer. RowHammer was worse in a bounded temperature range. And when we look at the DRAM cells that are vulnerable to RowHammer and row press, the intersection is quite low actually, and they behave differently. So in this paper, we show a real system demonstration, and the key idea is to send more read commands to the same row. So when you open up a row, you have many columns in this row, right? So you can, with some interval, you can send some read requests to different columns in this row. And as a result, your memory controller will keep that row open because there is a very good hit rate and the latencies are working well. the memory requests are serviced like in a very short amount of time. Everything is great. So memory controller will just keep it open. And then you will get bit flips, basically. Yeah. Here, if you send only one read command to a row, yeah, go ahead. Yeah. So if you have that relaxed refresh mechanism implemented, yes, you can keep it open up to like 70 microseconds. And here, if you just send like one read request, it means RowHammer, right? And then, yeah, we didn't see any bit flips, and we kept increasing like how many reads we send, how many different columns we read in a row. And then once we reached like 32, 48 reads, we observe like our bit error rate increases a lot. So here we have like 83 different bit flips in the nearby rows. And this is just like a showcase for as a like proof of concept, right? This is not really a rigorous study. And if you want to, do a more rigorous work on real systems, you're more than welcome. You can directly talk with Hasan. And he will be here in some weeks, I guess, to give another lecture. Yeah, RowPress can induce bit flips where RowHammer cannot in this kind of system. And the reason that you don't see any bit flips for RowHammer here is that your target refresh mechanism actually works well in this situation. It mitigates bit flips. So it protects against RowHammer, but RowPress is something new and it cannot. Okay, so how can we modify our existing mitigation mechanisms? Basically, we need to make them more aggressive. We need to configure them for lower activation thresholds. And hopefully it will not go to like one activation, but the trend seems like it will get lower and lower, right? So maybe with one activation in 70 microseconds, you will be able to induce some RowPress bit flips in some years. We don't know. So it's getting really challenging. So we basically need more aggressive solutions. And we did some study. We revisited two mechanisms, graphene and para. And we observed some like additional overhead on top of these original proposals. Let's say less than 10% for graphene, less than 25% or so for para. Maybe we have the numbers here. Yeah. So this is something. So we have an immediate solution, but it's definitely not really a super efficient, the best solution, right? It still induces like a lot of performance overhead. So we need better solutions again. So there are many more results in this paper, and it's artifactively related. Everything is online. You can check those out. I'm not going to go over these. And this is the RowPress paper, and these are the references you can access from the slides. And these are the DRAM Bender prototypes that we used for RowPress as well. And again, DRAM Bender references are here. You can just download it. For this one, you need to have an FPGA. But the good news is we have a lot of FPGAs. So if you want to work with us, we can give you some machines and basically some remote access, and you can just like start hammering rows, getting bit flips, analyzing them, trying different things. You just need to be like curious and dedicated. Again, two major directions. We need to understand bit flips, and we need to solve bit flips, and we need to focus on hardware errors, definitely, because these things are just like some vulnerabilities in the physics level, and they're exacerbated or leveraged in like many different layers in the system stack. Okay, so I already mentioned this work that does some tweak in the interface and makes DRAM and controller work better together. So I think I will not get into details, but just the key idea is that DRAM chip needs time to perform maintenance operations. And with the current interface, it doesn't have time. because every command is fine grain controlled by the memory controller. So this paper proposes to have a signal called actinec from DRAM chip to memory controller. This is a feedback signal, very simple. You send a row activation to DRAM chip, and if DRAM chip is busy running some maintenance operation, it tells you that it cannot activate. And then you try some other time later. And as a result of this, it actually alleviates a lot of problems that you might face when you implement new maintenance operations in DRAM chips. And we showcase for 3 different maintenance operations for periodic refreshes, RowHammer protection, and memory scrubbing. And we show that it actually achieves all of them really efficiently. And you can get the full talk from Hassan, the first author of this paper, in this YouTube link. Okay, this is the other work that I mentioned, that we reduced the refresh, the performance overhead of refresh operations. So I'm not going to go over it in detail because we will cover it later next week, I guess. So there are 2 types of refresh operations in DRAM. One of them is periodic refresh, the other one is RowHammer. And the key idea here is to hide the refresh latency by refreshing some rows while accessing other rows in the same bank. How we do that? It's similar to, it's based on the insights that you actually saw in yesterday's lecture. So you can actually do this act command sequence, if you remember from compute DRAM, to activate 2 rows. And if these 2 rows are in different subarrays in the same bank, then these don't share charge, and you can refresh one while accessing another one. So this is the main idea. And by doing that, you can overlap the latencies and you can save some time. And this can reduce the performance overhead of the existing RowHammer mitigation mechanisms a lot. So we show that on real chips that it works. And we design a mechanism that actually handles all these periodic refreshes and RowHammer refreshes. And we show some great improvements on top of the prior work. So periodic refreshes can induce a lot of performance overhead, and we can alleviate a great part of it. A similar case for RowHammer defense mechanisms, para is a showcase here. And there are more things in the paper, of course. And you can check this lecture. And I will also talk about this in detail in one of the next week's lectures. Okay, so we want main memories to be more robust in the future, but DRAM is becoming less reliable, and this is because of scaling, and there are a lot of security vulnerabilities, and this is also the case for DRAM flash memory and some emerging technologies as well. And there are many errors detected in the field, and there are many mitigations, but we need to do more. And this is a good example for like flash memory. We made some progress, but for main memory, there is more progress to be made. And if we have intelligent memory controllers, we can avoid many failures and enable better systems. For that, we need to understand, architect, and design and test real chips. And infrastructures are really important. The good thing is we have the infrastructure here, you can just use it. So I don't have so much time, but I'd like to show you some bridge photos again. We started with Galloping Gertie. It had some resonance issue in 1940 because of some bad design or bad engineering or bad execution of the project. Because of some reason, it got collapsed, right? And this is really a devastating accident. Luckily, this was in 1940, and we don't have this anymore. But in 94, we had something similar. So I guess 94 is still okay. It was like almost 30 years ago, and we didn't have like even good internet at that time, right? Technology was bad. But oops, 2007 again. We have like a lot of advancements in technology, in the construction technology as well, methods, everything is good, but we still see these collapses. A more recent example is from 2018. It's like it collapsed on top of these buildings, right? It's devastating. But it should be okay by now, you say. But in last year, there was another bridge collapse. And this one is in Pittsburgh, actually. This is like the steel center. This has been the steel center of maybe the whole US, maybe the part of the US, but really a great center in world scale as well. So you would expect them to build great bridges. But yeah, so these things happen, right? So we need to be prepared for, I mean, we cannot be prepared for bridges as computer engineers, I guess, but we can build our computers to be more robust against like this kind of failures. That's why we need intelligent memory controllers to avoid such failures. And I'd like to remind you this like 2013 paper that talked about memory scaling issues, and we still have the memory scaling issues after 10 years. And there was some interest in industry. It's faded away a little bit. Nowadays, again, industry is coming back to this, handling these scaling issues in the public domain as well. Yeah, we already showed this ST Hynix paper. So it's quite interesting and important. So, okay, some final thoughts on RowHammer. I guess I will make it on time. Great. So you can think of RowHammer errors as like sort of Byzantine failures, because they're characterized by some undetected erroneous computation, and it's the opposite of fail fast, right? So it's like you can have error, you can have no result. These can be silent. You don't know if they're malicious or, you know, maybe unintended. And yeah, so I guess it's at the end it boils down that it's quite difficult to detect some RowHammer attacks similar to Byzantine failures. There are a lot of things that are obfuscated from you, and so you can do everything to avoid them. But yeah, so it becomes quite challenging, especially with the newer version generations of DRAM chips. And yeah, I just kept this because Professor Mutlu also has this, so it's a fun read. So please take a look at that as well. But more importantly, of course, yeah, we need to focus more on RowHammer and RowPress and whatever comes next. We don't know yet. So before RowHammer, people were still exploiting the hardware failures to attack systems. So here, for example, they heat up some parts of the system to attack a virtual machine, this kind of side channel with physical access. But with RowHammer, actually, you don't need this physical access. Basically, you need a simple memory error, and you can easily induce it by doing something on software with JavaScript, right? It's just a web page. You open it, boom. Okay, so yeah, and another reminder about this retrospective. So, RowHammer is particular in the sense that it over the years it helped setting up a new mindset and renewed interest on hardware security attack research, because real memory chips are vulnerable, and this is a hardware solution, hardware problem, and it needs to be solved around this level in architecture as well. So there are many RowHammer attacks coming up, and there are many RowHammer solutions, but there are not enough. So we need more, actually. We need both more attacks and more solutions. Attacks help us understanding the dynamics more and covering the corner cases in the public domain. It's really important. So RowHammer shows that general purpose hardware is fallible in a widespread manner. Its problems are exploitable, and it attracted more researchers to look into these hardware failures. And it is not a coincidence that the people who discovered Meltdown and Spectre also worked on RowHammer before. So their domains are different, their dynamics are different, but these kind of vulnerabilities and basically security vulnerabilities have something in common. The hardware is vulnerable. So memory reliability is reducing, and it opens up new security vulnerabilities. They are very hard to defend against. So RowHammer is a prime example of how a hardware failure can be widespread and exploited in the system level, right? So there are some bad news that RowHammer is getting worse. Now RowPress as well. And good news is that we have a lot more to do. We need to understand more. We need to solve in a better way. And we need to develop principled methods, methodologies, solutions, etc. So we want to discover new bed flips, fundamentally fix them, and build more robust systems for future. This is, I guess, a bunch of people's ongoing research in our group. And we plan to invest on this more as future work as well. So you're more than welcome if you want to, investigate with us, and if you want to propose your own solutions. Yeah, we are here to basically realize your ideas. Please don't hesitate to contact us. And yeah, there's a reminder of this retrospective paper. You can just take a look at these papers, and all the reference papers, talks, and artifacts are available in this, especially the first link. If you go there, like all these links are available in the list, so you can just check all of them. And you can go to GitHub page to just like clone a lot of our resources, and it will give you some good hands-on starting point about RowHammer and RowPress as well now. So a final reminder about the upcoming seminar on Tuesday at 6 p.m. So Professor Lee will talk about how does one bit flip corrupt the entire deep neural network, and what can we do about that. She has very good insights, and we have a lot of overlap in our research interests as well. So yeah, please join, and don't also hesitate to ask questions. Just like you can get involved. It will be really beneficial for all parties. And this is the end of my slide, and I still have 3 minutes. Any questions? So you're talking about ambit, right? So you simultaneously activate multiple rows, and now you're saying that, okay, maybe there are more victims around these rows, and now I have like 3 rows open. Yeah, that definitely would induce some read disturbance in nearby victim rows, but I'm not sure how bad it is for ambit's case, because in ambit your purpose is to perform a lot of operations in a very short amount of time, right? So you keep doing that like triple row activations, and then you pre-charge, and you do another triple row activation because you immediately need to do another operation. So I think if you want to use that as an attack, you can just like, if you have ambit enabled in your system, you can just perform triple row activation, wait for a lot of time. It can be a fantastic attack. If you're talking about some benign usage of ambit, I think it wouldn't be the case, because you need to close it and then open another row. And usually this happens, yeah, that can be a problem. So when you have ambit kind of competition, usually you have dedicated rows in a different part of the bank. So the rows that you keep opening simultaneously are like in a like quarantined physical region, right? So they shouldn't affect the other rows in the bank. Maybe they can affect like nearby rows, let's say you have 16 rows or 32 rows in that region, the other rows are affected. But it's also likely that you will soon like open those rows as well. It's quite a good question actually. Yeah, so I guess in the benign case, you wouldn't observe any bit flips. But if you have that system and you use that functionality, I think that can be a good attack. You manipulate the computation, you change the result. Yeah, I can see that it's having some impact. Yes, yes, exactly. That's a very good point. So the first RowHammer program was just like a proof of concept, some demonstration, right? So they did it with CLFlush. And Google Project Zero was also doing it with CLFlush. And that instruction was in like some systems was allowed for some other users other than a super user as well to, perform. And then as a precaution, they made it like sudo only. But then we started seeing a lot of other attacks that actually do not even fetch any data to the cache. So there's this engine called direct memory access engine. It's like outside of the cache hierarchy, nearby the memory controller. So let's say you have some network chip in your computer's periphery, and then some packets are coming, right? So those packets don't actually go to the cache. They just like directly go to the memory. Or, for example, there are some specialized move instructions in some Intel ISA, and they allow you to give some like non-temporal hints. So as a programmer, if you know that, so this is just like some extra functionality that ISA gives you. If you know that, you will use some data, but you will not reuse it sometime soon, and you don't want to pollute your cache, you can pass some hints with some instructions, and those pieces of data is not actually fetched into the cache. So in case of RowHammer, if you're using those instructions, you don't have to flush them. So there are things like that. And also there are some other words that force cache evictions without using CLFlush. And how you do it is basically, if you're familiar with like set associative cache, you have like a limited number of slots for some given row address, right? In the cache hierarchy. And once you fill those slots and you want to fetch a new data, you need to evict some part of it back to the memory. So if you make it dirty, evict it. So basically, if you craft a smart enough access pattern, you can force your accesses to naturally keep evicting some cache lines. And this doesn't happen in benign case usually because the system is designed according to that. But if you're a malicious user, you can actually craft it in that way. So there are also demonstrations of those. So your point is correct. Like CLFlush was the first thing that these people kept doing, but it was prevented, and there were some other ways to bypass it again. Other questions? Do we have any questions online? Okay. Well, we exceeded our time. I'm sorry about that. Thanks a lot for your participation, and don't forget about this seminar again. Please attend. And yeah, have a great weekend.